Welcome to physics class on magnetism and matter, chapter 5 of CBSE class 12. In today's class, we will try to cover the following topics. The first one is bar magnet and its properties, current loop as a magnetic dipole and dipole moment, current solenoid equivalent to bar magnet and its dipole moment, magnetic field due to a magnetic dipole, terrestrial magnetism, and lastly we will discuss about elements of Earth's magnetic field. So first let's try to have or learn the properties of a bar magnet. A bar magnet has two poles, north pole and south pole. A freely suspended magnet aligns itself along north-south direction. Unlike poles attract and like poles repel each other. Magnetic pole always exists in pairs, that is, pole cannot be separated, or you can say that monopole never exists. A magnet can induce magnetism in other magnetic substances when brought near to it. A magnet attracts magnetic substances like that of ferromagnetic substances like iron. Repulsion is a sure test for a magnet. Now when you bring an iron rod and if you try to bring a magnet toward it, then both the poles will be attracted to it. That means when you bring closer the north pole toward the iron rod, your magnet will be also attracted toward the iron rod. When you bring closer toward the south pole toward the iron rod, then also it will be attracted. So we can't judge that iron rod is a magnet or not by simply having that force of attraction. But if you try to bring that a bar magnet, instead of bringing a iron rod, if you bring a bar magnet, let's take it like this side is north and this side is south. This is a specimen. Whether this specimen is a magnet or not, if you want to test it, then you need to bring a magnet. If you bring a magnet toward its north pole, nearer to that specimen, then what happen, this magnet will be attracted because there is of unlike poles here, south pole here, north pole here, so it will be attracted. But if you bring the other side of the this magnet, if you turn and if you bring it the other side, say let's take it like this, if you try to bring it your magnet toward the specimen which is going to test whether it is a magnet or not. So what happen if you change that north pole to south pole, and if you interchange like this and if you bring closer toward this specimen, then what happen, this south pole and south pole, we know that like poles repel each other. So what happen, this magnet will be repelled. So that means from here we can conclude that this specimen is a magnet. So we usually say that repulsion is a sure test of magnet or magnetization. That means you can only when this repulsion is there, then only we can say that the specimen or the material that is going to be tested is none other than magnet. If it had been iron rod, then what happened, whatever be the poles that is brought closer to it, it will be always attracted. So that attractive force or attraction can't give you the result that this specimen is a magnet. Only when repulsion is there, then only we can say that the specimen is what? A magnet. Why? Because unlike poles repel. Because of that, we can conclude that the specimen is a magnet. Okay. Yes, let's go to the next one. Let's see properties, the how to represent a uniform magnetic field. Now, uniform magnetic field we have been learning from that of the electric field. Also, electric field can be represented by what? Parallel lines. Uniform electric field can be represented by parallel lines equidistant from one another with an arrowhead. Is not it? Just like that here also in the case of what? Magnetic field, uniform magnetic field can be represented by parallel lines. Okay, equidistant from one another with an arrowhead will represent what? Uniform field on the plane of this paper, or you can say the screen of your that one that is observing now. It may be whether it may be your mobile or it may be what? A laptop. Okay, so this what? These parallel lines equidistant from one another will represent what is known as what? Uniform magnetic field, and the direction of the magnetic field will be in the direction of this arrow. Okay, now to represent whether the magnetic field is perpendicular to this plane, okay, then in that way what happen? We may have two directions perpendicular to this plane of the paper or screen, whether it will be directed inward or directed outward. So in order to represent that uniform magnetic field perpendicular to this plane, okay, plane of your paper or plane of your screen of your mobile, then what happen? It will be having just like an X mark. Okay, that will be just like this X mark. That means it is perpendicular to the plane of your screen or paper and directed inward. So what happen when you see an arrow from the back side? Then you will see the feathers of that arrow. The feathers of that arrow will be just like the X shape, X mark. Okay, it will be just like this X mark when you see that arrow. Okay, when you see this arrow like this from the back side, from this side, what happen? You will see only those feathers. Got it? Only those feathers, and that feathers will be in the shape of X. Got it? That mark, X mark, it is this one. Okay, you can have that mnemonic in that way. So if it is getting inward and perpendicular to the plane of the paper or plane of your screen, it will be seen or represented by such X mark. And being uniform, this will be also equidistant from one another. Okay, this will be all equidistant. See, it may be equidistant like this, in this way, whether it may be horizontal or vertical. Okay, and so this represents what? Uniform magnetic field perpendicular to the plane of the paper and directed inward. Got it? Yes. Now for the next one, if it is perpendicular to this plane of the paper or a screen, and if it is coming outward, that means getting outward means toward you, then what happened? Toward the observer, I mean, then it will be just with a mark. The arrow that is coming out toward you, you will see in the form of a small circle or a dot, you can say. So that how you can remember the mnemonics. Okay, so that will be what? Your if the arrow is coming outward like this toward you, no, you will see only the circular portion of the arrow. That is what it is here. What happened? The symbolic representation of that uniform magnetic field coming outward perpendicular to the plane of the screen will be what? It will be in the shape of the dot like this. Okay, yes, let's try to have that current loop. Okay, current loop, and it is current loop, it is acting just like a dipole, magnetic dipole, and we will try to learn about the what? Finding of the formula for magnetic dipole moment. So this is the current loop, okay, as a magnetic dipole. Let's see. Now you take a circular loop carrying current I. Okay, so this is the circular loop carrying current I, and this face is, this side is you are observing from this side, and this is behind. Okay, as per the diagram I will show you nicely here. So let's see that the direction of the magnetic field due to this circular current carrying capital I, and if you take it that this is the center of the circular, okay, coil or circular current carrying conductor, then the direction of what your magnetic field will be like this. You will easily see that this blue mark is not seen at this portion because this is covered by this circular conductor carrying current, okay, but here this is covered. That means this side is the watching side and this is the back side of the circular coil. Okay, this is a front side and this is a back side. You are observing from this side. So your magnetic field by your right hand thumb rule, it will be what, pointing in this direction. Okay, suppose if you are having observing this circular coil, you can also use your corkscrew rule also, but by simply looking from here, if the direction of the circular coil current direction, I mean the direction of the current in onto this circular conductor, if it is what, anti-clockwise, then that side will be acted as a north pole, and if that side of the circular coil the direction of the current is clockwise, then it will be what, south pole. That we have already done that one. Okay, this one here also same thing. So this side, the left side will be south pole and the right side will be what, north pole. Why? Because here the direction of the current you will see as anti-clockwise, but if you observe it from this side, then what happened, the direction of the current is what, clockwise, like this, right? So what happened, the direction of this side of the circular coil will be acted as a south pole and this side will be acting as north pole. We know that from a north pole of a bar magnetic line of force are coming out and it is getting inside toward the south pole, just like that. Okay, it is getting inside here, it is going away from here. So this side where the magnetic line of force comes out, that side of the surface will be acted as a north pole. Okay, this is the surface area, this side is the surface area facing toward the observer. Okay, and that side is behind the observer or behind the plane of this circular coil, that is behind, and this is the front side. So what happened, this will be the surface area of the circular coil and it will be denoted by capital A. Now just to find out the magnetic dipole moment, we need to have what, we need to know the direction, we need to know the magnitude of the current as well as magnitude of this what, I mean the surface area. We need to know magnitude of the current flowing through the circular coil and we need to know the area of this circular coil, okay, or circular loop you can say. So magnetic dipole moment is nothing but it is a strength of the dipole. Okay, the strength of the dipole, in this case it will be the strength of the circular current carrying what, coil, or that dipole. Your circular current carrying coil is just acting like a dipole. So we will say that magnetic dipole moment is nothing but this is a strength of that circular current carrying circular, okay, dipole. Now what happened, your magnetic dipole moment is denoted by capital M and it is a vector quantity, so we require an arrow there just to represent this is a magnetic what, just to represent this magnetic dipole moment as a vector quantity. So what happened, if it is a vector quantity then it will have its magnitude as well as direction, right? So the magnitude of this magnetic dipole moment will be equal to what, the product of the current flowing through that circular coil and the area of the circular coil. That will give you the magnitude part. So I into A, where I is the current flowing through that circular conductor and A is the circular or area of that circular conductor, okay, or loop. And what is this n cap? N cap is a unit vector in the direction of the magnetic field. Okay, if you try to curl your right hand, okay, with a forefinger stretching mutually perpendicular to your thumb, and if you try to curl in the direction of the current, okay, then the direction of a thumb will give you the direction of this end cap, or you can say it will be in the direction of the magnetic field B. Got it? So, or rather you can also think in that way, your magnetic dipole moment is from south pole to the north pole, okay, from the clockwise of the conductor current carrying circular loop to that of the anti-clockwise face side. Got it? And so its SI unit will be what? I, SI unit of current I is what? Ampere. SI unit of area is what? Meter square. So your SI unit of magnetic dipole moment of your circular current loop will be what? Ampere meter square. Now, as I have told you about the direction of these south pole and north pole, you can read from here also. You look it through here, whatever I have told you here, it is all here, okay. If it is anti-clockwise, the direction of the current onto that circular what loop. If it is anti-clockwise, then it will be acting as just like what your north pole. It will behave just like a magnetic north pole. And if it is clockwise, then this side will be acting or behaving just like a magnetic south pole, okay. Yes, let's see about the current carrying solenoid, and we need to compare with this current carrying solenoid with that of a bar magnet, okay. In the case of bar magnet, what happened? Not from a north pole, magnetic line of force are coming out or originated from the north pole, and it enters or terminates at the south pole, right? Just like that here also in the case of solenoid, current carrying solenoid, magnetic line of force will be coming out from a north pole and it comes toward the south pole, okay. But the difference is that in the case of a bar magnet, magnetic line of force is not there inside the bar magnet, but here in the case of a current carrying solenoid, this magnetic field is a continuous magnetic line of force is a continuous one. That means magnetic field is existed inside the axis of the solenoid. Got it? So what happens if a current is going like this, and if it comes here like this in this direction, okay, that means this side, when you observe from this side, the direction of the current will be what? Clockwise. If you observe it from this side, then the direction of the current will be what? Anti-clockwise from this side, okay. So this anti-clockwise direction will give you what? The anti-clockwise direction will give you north pole, and what? Clockwise direction of the current from this side, it will be acting just like a south pole, okay. Just like that, a bar magnet, okay, if you cut into different what pieces, then what happen? Your bar magnet will have north pole, south pole, north pole, south pole, like that. So why? Because if a bar magnet is dissected into two parts, then what happen? We know that magnet, okay, will always have two poles, okay. Monopole never exists, right? Suppose if you are having a bar magnet like this side is north pole and this side is south pole, like this. If you cut it somewhere here into two pieces, then this side, okay, will have two poles, south pole, north pole, like this. Another, this is north pole, so the other will be south pole, like this. So north pole and south pole, they it will be there. Just like that here also, if you cut it somewhere here, okay, then what happen? You will have this side as north pole and this side as south pole. For this loop, what happened? This side will be south pole and this side will be north pole. So likewise here also, in the case of solenoid also, all the turns, each and every of these circular turn will be just acting like a dipole, as we have just said, okay. So one side will be south pole, another side will be what? North pole. Just like that in the case of bar magnet is also there, okay. As I said, the difference is what? In the case of the solenoid, what happened? Your magnetic line of force is a continuous one, but in the case of a bar magnet, it is what? It originates, magnetic line of force originates from the north pole and it terminates at the south pole. That much difference, okay, is there. Now let's see. Okay, now in the case of bar magnet, let's see. Now this is a bar magnet, okay, and there are two poles in a bar magnet, okay, just near the end, but inside the material itself there are two poles. One pole will be just here at one end of the right side. The other will be what, at the left side, but inside the material, but it is very close to that end. Okay, this will be the what, south pole. So there are two poles in a bar magnet, okay, and the line joining, okay, the line joining these two poles, that line, imaginary line, we call it as what, the magnetic axis. Now the distance between the two poles, okay, the length or the distance between the two poles of a magnet we call it that as what, magnetic length of the magnet. This magnetic length is less than the actual length of the bar magnet. The actual length of the bar magnet we call it as geographic length. Okay, so let's see. And now what happened, this capital M that I have just shown you, this is nothing but this is a dipole moment of a bar magnet. What is this dipole moment? Just like that of the current, circular current loop, your bar magnet also has its own strength, and we call it that strength of the bar magnet as dipole moment of a bar magnet, and the dipole moment of a bar magnet is denoted by capital M. Okay, by capital M, and your pole strength is denoted by small m. Okay, the pole strength. So that pole strength will be here at each pole. Okay, one will be here, another will be here at this pole. Got it? So what happened, the magnitude of the what, magnetic pole times the magnetic length, we call it that magnetic length, or if it is denoted by only a what, single L, then will not be here. If your magnetic length is denoted by L, this magnetic length from one pole to another pole, then the product of these magnetic pole strength times the magnetic length, we call it these as what, dipole moment. Dipole moment is a vector quantity and it will be acting from south pole to north pole. Okay, it has a it is having what, direction. So its direction will be from where to where, from south pole to the north pole. Okay, now let's see. What about the geographic length? Let's see, this is a geographic length, the length of the bar magnet, we call it that as what, geometrical length or geographic length. Okay, yes, the distance between the two ends of the what, bar magnet is called as geometric length of the magnet. Okay, but you see that these poles are very close to that of the end of the bar magnet. The ratio of magnetic length and the geometric length is close, or it is nearly to 0.84. That means these two poles are very close to the ends of these sides. Okay, yes. Now magnetic dipole and dipole moment, as I have already mentioned you, in some textbook, instead of taking this dipole length or your magnetic length, okay, as what, twice L, instead of twice L, it may be taken also as L, but this is only just a matter of symbolic notation. If you take it that bar magnet somewhere here like this, the poles are here. Okay, these are one of the pole, you may take it this as south and this as north. Suppose if there is a pole here If there is another pole here, then the distance between these we may take it as L or twice L, so that what happened from the center, okay, from the center of the bar magnet, if you take it this as L, the other side as L, like this, then what happened, the total length will be what, the total what magnetic length will be what, L plus L means twice L. So the product of these, what pole strength M, okay, this pole strength M times the magnetic length, this will give you what is known as your dipole moment of the bar magnet. Okay, yes, and as I told you that it will be directing from south pole to the north pole. It is a vector quantity, but the magnitude will be the product of this what pole strength and the distance of separation of the two poles, or you can call it as what magnetic length, right? Now magnetic dipole moment, as I said, it will be equal to what, the pole strength times the magnetic length. And what is this L? L is nothing but it is a unit vector directing from south pole to the north pole. Okay, as I said, it will be all here. Now let's see about the terrestrial magnetism. Now before knowing that, let's try to know some of the terminologies. Okay, the first one is what, geographic axis. What is this geographic axis? The geographic axis is a straight line passing through the geographical poles of the earth. That means from the north pole to the south pole, if you draw a line, okay, passing through this geographic south pole and geographic north pole, that line or that axis is known as what, geographic axis. And this axis is nothing but, this axis will be the axis of rotation of the earth. It is also known as polar axis. Why? Because this axis passes through both the poles. Okay, poles means north pole as well as south pole of the earth. Okay, why we call it this geographic? Because this is the axis passing through that geographic what, north pole and south pole. Geographical north pole and south pole is different from that of earth's magnetic south pole and north pole. Okay, we will come later on. Now what is this next term? Next term will be what, geographic meridian at any place. Why we say at any place? Because this geographic meridian will have a different at different places. Okay, it is a vertical plane passing through the geographic north and geographic south poles of the earth. Okay, it is the vertical plane passing through the geographic axis, that plane which passes, okay, or that vertical plane, I should say, that vertical plane passing through this geographic axis, we call it that as what, geographic meridian. Now what is this geographic equator? Let's see. Geographic equator, it is that equator that we have learned in our geography. Okay, that is known as what, equator. What is this equator? It is a great circle, okay, on the surface of the earth in a plane perpendicular to the geographic axis. Okay, and it will be in the middle point of that line, or between that of the line geographic axis. If you started from the north pole to the south pole only, then it will be at the middle point of the line joining from the north pole to the south pole, from the geographic north pole to the geographic south pole. At that middle point, if you have a what, perpendicular plane, and that perpendicular plane will be on the surface of the earth, and that, okay, circle which is on the surface of the earth will be what, that will be known as equator. Okay, and what happened, let's see, this equator, the equatorial plane must be perpendicular to that geographic axis. Okay, this is very important. Now next, let's try to have that magnetic axis. Now you will know that as I told you that the geographic axis and the magnetic axis are different. Suppose if you have your earth, suppose like this, let's see, let me draw that diagram. Okay, small one. Suppose this is your earth, for example. okay, and your geographic north pole is somewhere here and geographic south pole is somewhere here. This is the axis of rotation of your earth, okay. This is what the first one. The first one is what? Your geographic axis, okay. What is this? Your geographic north pole, okay, this point I mean, and this point is what? Geographic south pole. So that line passing through this geographic north pole and geographic south pole, we call it this as geographic axis. And at the middle point here, somewhere here and perpendicular to it, that line that is drawn perpendicular to the geographic axis, that line on the surface of the earth, we call it that as what? Equator. This is what? Geographic equator. Got it? And this will be what? Equidistant on to these different points. You may take it somewhere here or somewhere here, somewhere here. This will be equidistant from the pole. If you take it somewhere here also, that point will be equidistant from the pole. Got it? So what happened on to the surface? Okay, if you draw that circle will be the largest circle, and we say that that is a great circle, okay, on the surface of the earth. Got it? And this plane of this equator must be what? Perpendicular to this geographic axis. And now a plane perpendicular, okay, a plane perpendicular to this what? Geographic axis at a point, that plane we call it as geographic meridian, okay. When you say meridian, that you have to remember always that vertical plane, okay, parallel to geographic axis, we call it that as geographic meridian. And now let's go to the magnetic axis. Now it seems that your earth is just like a huge magnet, okay. In that way, what happened if you take it that your earth as a huge magnet, and what happened, your earth's magnetic north pole and south pole will not be having a line with the what? Geographic axis. If this is the earth's magnetic, okay, it seems that I am drawing as a bar magnet, okay, just to have that what? Similarity of the magnetic field, okay. This will be acting as what? Your earth's, let me denote it by E only, earth's magnetic, and this will be what? South pole, okay. And this side will be acting as earth's magnetic north pole, okay. Don't think that in onto that side of the geographic north pole your earth's magnetic north pole will lie there. So what happened for the earth's magnetic field, your your magnetic line of force will start from the north pole and it ends toward the what? Geographic north pole. From the geographic south pole, it seems that your magnetic line of force originates and it enters here inside the what? Your geographic north pole, like this. Got it? In this way. So that axis passing through this what? Earth's magnetic south pole and the Earth's magnetic north pole, that axis passing through this Earth's magnetic south pole and north pole, we call it that axis as what? Magnetic axis. Clear? And this angle will be around what? The axis, that means your geographic axis and this magnetic axis, okay. This will be of around 17 degree. They are not lying just like what? One above the another, okay, not parallel to each other. They are tilting of how much degree? Around 17 degree. And now what is meant by magnetic meridian? When I say meridian, you should think of about that vertical plane, okay. Magnetic meridian is nothing but this is the vertical plane passing through what? The magnetic axis. We call it that as magnetic meridian. When I say magnetic equator, at this middle point of that what? Magnetic axis, if you draw a perpendicular plane and that plane intersects your what earth surface, then you will have a circle somewhere here onto the surface of the earth like this, right? That equator is known as what? Magnetic equator. Why? Because this plane is drawn perpendicular to the magnetic axis. Got it? Yes. Let's see the definition part. Okay, I will just rub it out and let's see. So what is having the magnetic meridian? It is a vertical plane passing through the magnetic north and south pole of the earth. That means it is a vertical plane passing through where? Magnetic axis. That is the meaning. Okay, and let's see about the magnetic equator. It is a great circle on the surface of the earth, okay, in a plane perpendicular to the magnetic axis. So all the points on the magnetic equator are at equal distance from the magnetic pole, just as we have in the case of what? Geographic equator. Okay, like that here also all those points on the magnetic equator will be equidistant from the magnetic north pole or south pole. Now there are three elements, okay, we call it that as Earth's magnetic element. Let's try to learn about that. Okay, the first one is what? Declination. The second one is dip or inclination, and the third one is what? Known as horizontal component of Earth's magnetic field. So let's try to learn about these three different Earth's magnetic elements. Why these Earth's three Earth's magnetic element are important? Because after knowing these three elements at a particular point, then you will know all the behavior and all the properties of the magnetic field, Earth's magnetic field at that particular point. Okay, now to know this declination, let's try to know first what is geographic meridian and what is magnetic meridian. If you know those two meridians, geographic meridian and magnetic meridian, that angle between that magnetic meridian and geographic meridian, that is known as what? Declination. So let's see what is this geographic axis. Okay, geographic axis means that axis passing through geographical south and geographical north point. That axis we call it as geographic axis. A vertical plane, okay, passing through this or parallel through this, we call it that as geographic meridian, right? Yes. Another axis known as magnetic axis. That axis passing through Earth's magnetic south pole and Earth's magnetic north pole, we call it that axis as magnetic axis. And a plane passing through this, okay, rather that plane must be what? Vertical plane. So a vertical plane passing through this magnetic axis, we call it that magnetic axis, that plane as what? Magnetic meridian. Okay, magnetic meridian. So your angle of declination is nothing but this is the angle between the geographic meridian and the magnetic meridian. That angle we call it, okay, the angle between these geographic meridian and the magnetic meridian, that angle is known as what? Declination at that place. Okay, so it varies from place to place. It will not have the same value. So this is denoted by theta. Your declination is denoted by theta, and it is the angle between the geographic meridian and the magnetic meridian at that place. It varies from place to place. Okay, and on the map, if you try to join all those points having the same declination, those lines are known as isogonic lines. Okay, what are isogonic lines? Isogonic lines are the lines on the map, okay, which join all those places having the same value of declination. Got it? That line is known as isogonic lines. And those lines drawn on the map where there is having zero declination, we call it as agonic lines. Okay, this is known as agonic lines. Agonic lines are what? Agonic lines are the lines on the map which join okay, all those points on the map having what? Zero declination. Got it? Now let's go to the dip or inclination. Now what happened just before that one, if you try to have, okay, your north pole and south pole, okay, of a bar magnet, okay, and if that bar magnet is allowed to move about a horizontal axis, okay, if your bar magnet is allowed to move about a horizontal axis, now when you use what compass needle, we usually place that compass needle parallel to the ground, okay. That means your compass needle will move to and fro like this. Got it? So what happened? That compass needle moves to and fro about a vertical axis in that case. Okay, just to find out the direction, we usually have that compass needle of whose face is what? Parallel to the horizontal ground. You keep it like that. The plane of the watching side is kept parallel to the horizontal, right? Parallel to the horizontal. So what happened? In that case, you will try to find out direction north south direction like that, no? If you know that north south direction, then east and west can be also very much easily determined. You can easily determine it. But in this case, what happened? You need to place that plane of that what compass needle vertical, and that vertical plane must be also parallel to this magnetic meridian. And when you place it, that magnetic compass needle parallel to this magnetic meridian at a place, what happened? On the northern hemisphere, your north pole will be pointing toward the what? Making some angle inside the earth like this, toward the earth, okay. That direction is nothing, the direction of that north pole is nothing but that will be the direction of the earth's magnetic field. But in the case of southern hemisphere, what happened? Your south pole will be pointing toward it, okay, making some angle. So that direction of the magnetic field, in our case, it will be somewhere here. Let's see. Okay, so this is a dip or inclination. For that, what happened? Your compass needle, suppose for example, if your compass needle is placed somewhere here like this with its plane parallel to this compass needle, okay, parallel to this magnetic meridian, I mean, then your south pole of the bar compass needle will be on this side, and that of the north pole, I mean north pole will be on this side and south pole will be on this side, okay. It will allow to move onto this plane, okay. Previously, suppose if it is here like this, north pole on this side, south pole on this side, then what happened? This will be in the direction of your north pole and this will be in the direction of south pole, okay. If you place your compass needle parallel to the horizontal, okay, but instead of keeping that plane of this compass needle horizontal, you try to place this plane of this compass needle perpendicular or vertical, okay, so that what happen, this compass needle will allow to move about this horizontal axis, okay, about this axis, and it will be in the what? Magnetic meridian. So this compass needle will allow to move to and fro in this plane only, okay, in the plane of what? Magnetic meridian. And after moving for to and fro for some time, and it will be settling down here at some angle, that direction of this north pole will be nothing but it will be the direction of the earth's magnetic field. So what happened? The direction of the earth magnetic field is making some angle, okay, and it will be downward in the case of northern hemisphere, and in the case of in the northern hemisphere, your north pole will be pointing downward. In the southern, at a point on the southern hemisphere, your north pole, instead of north pole, the south pole will be pointing toward the earth, okay. Now this is the direction of the horizontal direction, and this is the vertical. Got it? This is the direction of the magnetic field, and your angle of your dip or inclination may be defined as the angle between the earth's magnetic field, okay, your dip or inclination is the angle between Earth's magnetic field B vector with that of the horizontal direction in the magnetic meridian. Okay, not the horizontal direction in any direction, but it should be the horizontal direction in the magnetic meridian. Got it? So that angle between the Earth's magnetic field and the horizontal direction in the magnetic meridian, that angle, we call it that angle as angle of dip or inclination, and it is denoted by del. Got it? Now if you try to resolve this B into two rectangular components, one along the horizontal and another along the vertical, and that can be denoted by V BV, that means Earth's magnetic field, okay, in the vertical direction, and Earth's magnetic field in the horizontal direction, B heights. Okay, so that what happened, that B heights, okay, let me draw it again. Okay, so this is your B, no doubt, and if you try to resolve it, this what B into two rectangular components, one along the horizontal, that one we call it that as B heights. That means component of B along the horizontal, that is denoted by B heights. The component of B magnetic field, Earth's magnetic field in the vertical direction, that may be denoted by BV. Okay, and we know that your B heights, okay, this will be equal to what? B cosine of what? Del, right? And your B vertical will be equal to what? B sine of del, right? So this will be used up in the latter case, but first let's try to what, define those terms first, and then we will come back again. Okay, so your dip or inclination, after resolving that, what happened, the two components BH and BV will be there, and so what is this, what, dip or inclination, you can also define that it is the angle between what, the Earth's magnetic field and the horizontal direction in the magnetic meridian. Okay, it is that one, it is given here. Now let's see, it is 0. Okay, this angle of dip is 0 at equator and 90° at the poles. So what happen if you go toward the equator, then this angle of dip will keep on decreasing, this angle will keep on decreasing, and what happen at equator, the angle will be 0. That means your Earth's magnetic field, rather your compass needle in the vertical plane, it will come up and it will be lying here at the horizontal direction like this. Got it? So then what happen, angle of dip will be equal to 0 at the equator. But when you go from the equator toward the northern pole, okay, toward the northern geographical northern pole, then what happened, this angle will keep on increasing, and when you reach at the pole, the north pole of the bar magnet or compass magnetic needle, you can say the north pole of the compass needle or magnetic needle, it will be aligned here like this. That means angle of this, okay, dip or rather your del will be equal to 90° at the poles. Okay, same is the case when you go to the south pole also. In that, what happened, instead of this north pole, what happened, that south pole will be pointing here like this toward the earth. Okay, just vertical. So what happened, angle of dip will at that point also, it will be what, 90°. Got it? So angle of dip is equal to 0 at equator and 90° at the poles. Okay, and those lines, just as we did in the case of your declination, okay, those lines drawn on the map, okay, that have the same dip are called as isoclinic. Okay, iso means equal, clinic means those of inclination, it comes from this inclination, so isoclinic. Got it? So those lines drawn on the map, okay, of the place having the same dip are called isoclinic lines, and those lines drawn, okay, on the map of those places having what, zero dip, we call it that as a clinic line. It is nothing but the magnetic equator, okay. And those magnetic equator will have what, zero value of this dip, okay. The dip or at the magnetic equator will have all zero value, right? Yes. Now let's see about the horizontal component, the third what magnetic elements of the earth, and it is denoted by BH. Now as I have said in that previous one, I will draw that diagram again and I will tell you, okay. Now in that previous slide we see that your earth's magnetic field is like this, B, right? And if you resolve it, this, suppose if it is the horizontal direction, then this angle is known as dip. So your horizontal component BH and the vertical component BV here like this, right? So as this is the del component, your BH will be equal to what? B cosine of del. That is what it is having here. And this will be equal to what? B sine of del. That is what it is having here. Okay. So what happened? This, if you take it somewhere here, then this B, 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 this is B, BH, BV, like that. So this BV will be, you can make it here like this also, BV. If you can shift it here, okay. So this is B, BV, and this is BH. Now as this BV and BH are the rectangular components, what happened? This will make a right triangle, right? So that what happened, your B square, this will be your right angle and this will be treated as hypotenuse. So the length of this hypotenuse side will represent your earth's magnetic field B. So your B square, by using your Pythagoras, B square will be equal to what? BV square plus BH square, right? Got it? So this is your BV, right? And this is your BH, right? So if you want to find out your B, then you have to take it the square root, okay? The square root of what? The square root of this. So your B will be equal to square root of BV square plus BH square, or you can write BH square as I have drawn, as I have done here also, okay? So that is what? The relation between the earth's magnetic field and those of the what? Its component, okay? BV, BV and BH, vertical component and horizontal component. Got it? Yes. Now the last one is what? That of what we call it as tangent law. So in this tangent law also, it is very much similar to this what we are having here in the case of horizontal component, okay. Now if you try to divide this vertical component, okay, if you try to take the ratio of vertical component of the earth's magnetic field to the horizontal component, then this will be what? Just B sine of del, right, divided by B cosine of del, right? So BV can be cancelled. Sine del by cos del will be what? It is nothing but it will be equal to tangent of del, okay. It is very much similar to this with the tangent law also, okay, but the statement is little bit different, okay, but it is almost same with this one. Now let's see about that of the tangent law, okay. In the case of tangent law, what happened? If a magnetic needle is suspended in a region of uniform, okay, magnetic field which are perpendicular to each other, suppose if your uniform magnetic field, one is acting here, another is acting here, so let's denote it by B1, okay. Another magnetic field which is also uniform, let's denote it by B2, and it is acting along this y-axis. So what happen if you place a magnetic compass needle, okay, magnetic compass needle into these two mutually perpendicular uniform magnetic field, then what happen, your magnetic field, okay, will be due to the combined effect of this, and so your compass needle will point somewhere here like this, making some angle, okay, with the horizontal direction. Okay, then what happen, this will be nothing but this will be the resultant of these two components, or rather these two magnetic fields. Okay, so your B can be also expressed as what, I mean B1 can be expressed as what, B cos of theta if this is theta, and then B2, which is a vertical component, you can think it in that way, then it will be equal to B sine of theta like this. So if you divided this B2 by B1, then it will be equal to tangent of theta, right? Similar to that, as I have said here, BV by BH will be equal to tangent of del. Got it? Like that, in that way. Let's see. Now if you are having a compass needle here, okay, and if this compass needle is placed inside two uniform magnetic fields which are mutually perpendicular to each other, then what will happen? Let's see. This is one of the uniform magnetic field denoted by B1, and another denoted by B2, so they are perpendicular to each other. So what happens, your compass needle points in a particular direction, and that direction of the north pole is nothing but the resultant of this B1 and B2. Okay, with this B1 and B2, let me show you again like this. See, this is the first magnetic field, you can take it as a horizontal magnetic field, and this is also uniform. Okay, B1 is a uniform magnetic field along x-axis. Then B2 is also one of the uniform magnetic field along y-axis, and then you will see the compass needle is pointing or tilting toward like this. That is nothing but this is the direction of the resultant magnetic field due to this B1 and B2. Okay, this B is the resultant magnetic field of B1 and B2, and it is making an angle theta here. Got it? So then what happened, your B1 will be equal to what? B cosine of theta. B2 will be equal to what? B sine of theta. Okay, and if you divided that two, then it will be equal to what? B2 by B1 will be equal to what? Tangent of theta, right? So let's see the statement. Okay, if a magnetic needle is suspended in a region where two uniform magnetic fields are perpendicular to each other, okay, the needle will align itself along the direction of the resultant field of the two fields at an angle theta, such that the tangent of the angle is the ratio of the two fields. So your tangent of theta will be equal to what? Ratio of the two fields means B2 by B1. And how it is coming, I have already shown you that B sine of theta divided by B cosine of theta. So when you cancel that BB, you will have as tangent of theta like that. Okay, so this is what we call as tangent law, and with this we will come to the end of our today's class. Thank you.